welcome again to this new lecture of solar photovoltaics principles, technologies and materials. So, a lot of it now is based on solar cell technologies. So, I would recommend a few books to you. So, you can have for example, you can have a look at handbook of although I might have told you this earlier, but Science and Technology by Luke and Hegdes. This is a nice book, and then you can also look at from the perspective of thin film solar cells. You can look at thin film solar cells by K.L. Chopra and S.R. Das, and you can also look at physics of solar cells by Jenny Nelson. In addition, there are a lot of papers, reviews and articles which can be dealt with, especially for third generation. They are not present in the books, and there are a lot of other books present in the literature, so you can look at many other books. So, now let us just do a bit of a recap in the last, what did we do in the last lecture. So, in the last lecture we looked at basically started our discussion with silicon and monocrystalline silicon, as we know. So, silicon is present in basically three primarily forms. One is monosilicon, which is basically single crystal silicon. So, wafer is single crystal, there are no grain boundaries and grains. And then we have polysilicon, which we call as polycrystalline silicon. So, you have grains of silicon which are bigger, quite bigger than the thickness of the device, and then we have amorphous silicon. These are three major technologies that are present in the market, and these are thin films. Okay. And silicon, as we know, is a diamond cubic structure material. It has a band gap of 1.1 eV. It is an indirect band gap semiconductor, and as a result it has poor absorption of light. Okay. And one uses, in the solar cell context, one uses N silicon and P silicon. Both of these are made by doping. So, N silicon is, for example, made by phosphorus doping. This could be made by boron doping, and this doping leads to reduction in the carrier mobility as well as lifetime. However, P doped silicon has higher lifetime. So, tau N in P silicon is larger than tau P in N silicon. So, carrier lifetimes are a little larger in P and N silicon, P silicon over N silicon. As a result, P silicon is the base, N silicon is the typically the emitter. So, device form is like this. So, you have N silicon on top, P silicon at the bottom, and the radiation comes from top. So, important thing in this configuration is, since silicon is an opaque material, most of the and it is a light absorber, the kind of contacts that you put on top of it, that is very important. So, generally the way silicon is made is, silicon is made with, so there are certain design considerations that we need to follow to make a good device. So, what are the design considerations? The first design consideration is the light which is incident on the solar cell. So, maximum absorption of light into the solar cell. Okay. So, what does it mean? It means, one, you reduce the reflection losses, and that we also see in quantum efficiency, right. So, reduce reflection losses, which means you need to do some sort of things to do some sort of modifications to the surface, and then also you need to design your top electrode such that light is not blocked. Okay. And then you need to, and of course silicon is fixed, right. So you can't change the material, but you can adopt strategies so that you can have maximum absorption into the. So what we do is that in that case optimize the device thickness. Okay. But, and this is with vis-a-vis loss of current, all right, because if you can make it very thicker, then recombination becomes a problem. So as a result, you need to basically optimize the device thickness so that you have maximum absorption and maximum current. So there is optimization between the two. And then second thing is, how do you improve the strategies to improve the collection of charges and minimize the in this thing. We can also add one more thing in the top thing, is to improve the light coupling, improve the into the device. And then how do you improve the collection of charges and minimize the recombination losses? And we have and third finally we will have how to have effective collection and extraction of carriers at the electrodes. The collection of charges here means basically in the top, in the second point, is your photon gives rise to exciton, and exciton then converts into electron hole pair. So we would like to maximize this process, and then which is going into free, so and then we have dissociation, right. So we must have strategies to maximize this process. That is, photon is absorbed, exciton is created, electron hole pairs are formed, and electron from hole pairs then get dissociated. So this is what we have to maximize. So these are certain design considerations that we need to that we consider in device fabrication. And as a result of various strategies, silicon efficiency as far as they are concerned. So silicon of as far as monosilicon is concerned, monosilicon efficiencies are of the order of 25% at the lab scale. They have achieved nearly 25% or maybe higher, a little bit higher, whereas in case of polysilicon, efficiencies are of the order of 22 to 23% at the lab scale. Perhaps 22% is the more accurate number over 23. So nearly 22%, they are not very fixed numbers, but nearly 22%. If I look at the correct numbers, yeah, so in this case it's actually the lab scale is 26.7% is the highest. Okay, this is as of 2017, and the multicrystalline has an efficiency of 22.3 is the highest, and this is from Kaneka, whereas this is from German manufacturer FSG ISC, I think is Forschungszentrum in Germany. Okay. So these are numbers that have been achieved after modifying various design considerations. This is the material, silicon material is same. I mean, you started with low efficiency, and today we are standing at 26.7 in case of monosilicon and 22.3 in polysilicon. It has come mainly through making modifications in the device and going through various design modifications, okay, going through several minute tiny changes in the devices which have led to significant improvement in the performance. So, now if we go to strategies to, for example, how do you first thing that we follow is, so we have this as a solar cell device, and on top we have N silicon, at the bottom we have P silicon. Okay. So, this N silicon is, of course, because N silicon is little thinner, so it's less than a micron, whereas this is about 300 to 400 micron. Okay. Now, this light comes from top here. First thing is to minimize reflection, and this reflection is minimized by use of anti-reflection coatings, and generally we have a bilayer of you can say, so on silicon you can have SiO2, and on top of that we have a layer of TiO2. Okay. So, this leads to improved anti-reflection properties of silicon surface. Okay. You can also provide ARC on glass. So, use of ARC is done both for silicon as well as glass cover on top. Okay. And there are various oxide coatings. So, these are basically anti-reflection coatings are oxides, nitrides, and generally they are deposited by processes such as CVD, PCVD, and so on and so forth, chemical vapor deposition processes, which are large area processes, and these layers basically reduce they are very thin layers, but they reduce the reflection losses. Second thing that is achieved is to do the texturing of the front surface. Now, texturing means, see, silicon, generally silicon wafer is this plane is 100, okay. This is 100 plane. 100 plane is generally cut flat, okay. So, it is pretty much planar surface. However, in silicon within 100, so if this is 100 plane, you will always have these 111 kind of planes, because it is FCC structured cubic material. These are 111 planes. Okay. If you do the etching of silicon in such a manner, so that you are able to expose these 111 planes in such a fashion, so that this is removed and what you are left with a surface like this. So, we have a surface in which we do not, although these planes are all 100 planes, on the top, because of chemical etching, we have preferentially removed the atoms from certain planes, so that 111 plane is exposed. So, these are all 111 planes which are at certain angles to 100, you can calculate it is about 54.7 degrees. So, these 111 planes improve the optical absorption. So, when the light now comes, so in this case if the light came, it would directly get reflected. Okay. Here, if your light comes in this fashion, part of it will get absorbed, part of it might get reflected, it might go there, then it might go there. So, basically you have maximized the absorption of light by this surface texturing. So, this surface texturing can be done by chemical methods, by use of appropriate etchants or acids. Okay. This is one strategy that is adopted. Second strategy that you can adopt is to improve the contacts design. So, of course, one strategy is you have the surface, textured surface, and if you want to put contact on it, of course, you will have to put contact because you want to extract the charges. When you put the contact, if you put the contact like this, which is a metallic contact, okay. If you put a metallic contact like this, so this is metallic contact. Since metals are opaque, this is going to reduce light transmission. Even if you put a thin layer of metal with certain transmission, it is going to reduce the light transmission. Okay. So this is no, which means you can't completely cover the surface of silicon with the metal because it will block the light, even if it is a thin layer of metal. So another strategy that is useful to adopt is to use this kind of surface. So again, have textured silicon surface, and you use the contacts which are buried inside. So you have deep contacts. So you have contacts in this fashion buried inside the solar cell. So you have contacts buried at certain interval. So these contacts, so you have you maximize the interfacial area. Okay. So this is metal contact. You have to, of course, optimize the spacing between these two as well as the height h, so that you have minimum parasitic resistance losses, because if you make them too far, then your device resistance will increase, your collection will be poor. So there is a need to optimize the spacing and the length of these contacts and the depth of these contacts. But however, if you do this, then you do not compromise on the light absorption. Most of the silicon surface is still available for light absorption by directly coming in contact with the light without having any intermediate blocking layer to prevent the light from coming. So these are basically metal contact, basically N type contact, because underneath you will have N silicon. Okay. So in the vicinity of these contacts, the silicon is little heavily doped. So in the vicinity, silicon is N silicon, N plus silicon, and in the underneath it will be little lightly doped, less heavily doped silicon. So basically what we have a differential in dopant concentration in the silicon in the vicinity of contact. So if this is contact, if you zoom it up, in the vicinity you have higher dopant concentration, higher ND. In the region surrounding it you have lower ND. This helps to prevent the recombination near the contacts, and also it helps to make a good graded contact, because carriers will go fast towards the contact. So when you have this little gradient like in the dopant concentration, there is a gradient in the bands also. So carriers get slowed down as they reach the contact. So the surface recombination is little lower as compared to having a uniform doping around it. So these are certain ways to, and then of course you can also increase the device thickness, because if you increase the device thickness, we know that I is equal to I naught exponential minus alpha x. So if your x increases, your absorption will increase, right? Amount of light absorbed will increase. So transmitted light will reduce as your thickness increases. As a result, you can increase the device thickness. However, device thickness cannot be increased indiscriminately because of constraints with LP and Ln, right? Because these are finite numbers. So if you increase it too much, then you will have a lot of recombination in the device. As a result, the device thickness should be optimized. Vis-a-vis LP and Ln. and as I said, top contact coverage, the coverage area of the top contact metal contact has to be optimized. So, these are certain methods to improve the optical losses, to reduce the optical losses. And then of course, doping plays a very important role. Doping helps in, so high doping leads to high built-in field, right, high VBI, because VBI is proportional to ln of NaND divided by Ni square. So, if you have high VBI, you are likely to get high VOC also. So, this may lead to high VOC, but when you increase the doping, doping also leads to higher recombination, especially at heavy doping. So, if you plot the VOC, so this is for example doping concentration in per cc, and this is for instance your VOC in volts, and then we have here, let us say, the diffusion length, because diffusion length, okay. So, generally the diffusion length, so if I plot diffusion length as blue, purple, so this diffusion length goes down at higher doping level, okay, because the scattering increases, as a result your mobility decreases, your diffusion lengths go down, because your lifetimes go down. But on the other hand, your doping tends to increase the VOC, so your VAC tends to increase, but because of this change in the diffusion length, the VOC again reduces because your currents start reducing, and VOC, as we know, is a function of current also. So, as a result, there is an optimum VOC that you get for, there is an optimum window of doping at which you get maximum doping. So, you can say you have an optimum window of doping, and this is around you can say about 10 to the power 16 to 10 to the power 18 per centimeter cube, if you think of this base doping, okay. So, doping is so on the left hand side you have decreased recombination. So, at this, on this side you have lower recombination, because you have lower carrier concentration, minority carrier concentration is lower, as a result your recombination is lower. But on the other side you have higher recombination because of reduced diffusion length. So, there is an optimum that you need to work out, and this optimum is somewhere around this number in terms of VOC. Then of course, you need to again worry about the surface recombination to collect the charges efficiently. So, surface recombination, one thing, there are a lot of things people do. So, for instance, if you have a solar cell like this, right, you have N silicon, you have P silicon. So, what generally people do is that one, they make a layer of silicon oxide on the top surface. So, this is SiO2 formation on top, a thin layer of silicon oxide, which leads to surface passivation by suppressing the dangling bond density. So, that reduces the surface recombination. So, reduces surface recombination. Then we have, if you have contacts, let us say if I put contacts now, let us say these are my contacts. This is again another contact somewhere here. Contact has to be in touch with the silicon. So, oxide is at the places where there is no contact, okay, and oxide is transparent to light, so it does not affect the absorption. So, near the contact, generally if this is contact, underneath you have this region as we said is heavily doped. So, this would be N plus, this would be N plus, and this again keeps the minority carrier away from high recombination. So, there is less recombination. Okay. All right, as you apply the bias, the minority current increases and minority carrier concentration increases. So, you would like to prevent the recombination to have to reduce the recombination current. And then we also do heavy doping at the rear of the cell. So, this region is also little heavily doped. So, you can say this is P plus region, again reduces the surface recombination. Okay. And the reason basically is, suppose you have this if this is p type layer, let us say ECEV, okay, and in the bulk you have this as, let us say, Fermi level. When you heavily dope, the Fermi level goes down a little bit here. So, as a result, carriers find a more higher barrier for. So, basically in terms of holes, the going down is a barrier. In terms of electron, going up is a barrier. So, if you look at the N side, so I think it is more clear from the N side. So, let us say if this is the Fermi level, uniform Fermi level, but if you raise the Fermi level, so let us say the carrier is coming from this side. If you raise the Fermi level a little bit here, if this Fermi level is higher as compared to the Fermi level somewhere else, the carrier will face a little bit of barrier. This slows down the carriers, and as a result the surface recombination is lower. So, that is why there is a gradient in composition that is put near the surface, near the contact on the top side and again near the contact on the bottom side. Both of these keep the carrier away from recombination. So, recombination losses are reduced in both the cases, and this again is the contact on the back side. All right. So, this is what is done to improve the contacts, and a typical solar cell of a, so silicon, we have seen what kind of solar cell we can have. So, this is what is the design, overall design. Okay. So, on top we have N silicon, at the bottom we have P silicon. So, on this side, so this is let us say N silicon part. On the top we have contact fingers. So, the contact fingers will be somewhere like this, and you need to optimize their length and their breadth, so that you have optimized series resistance, because and you can't cover the surface too much because of optical losses. So, these are contacts. On top, similarly you will have a contact at the bottom. So, this is bottom contact, which is positive, this is negative, and this is about 300 micron, and this is about 0.2 to 0.3 micron. So, whole device is roughly 0.3 mm thick, and on top we have a layer of ARC, that is anti-reflection coating, and your light comes in this fashion. It will come from top and then it will get absorbed in the rest of the solar cell, and in the here you will form the depletion zone. So, you will have positive charges here and your negative charges will be here. So, this will be your depletion region, and since top is more heavily doped as compared to bottom, the depletion region is more in the P side than in the N side. N side is much more thinner. So, this is typically this is a typical design that you have for silicon solar cells, and we will now move on to the next lecture, in which we will talk a little bit about the multi-silicon solar cell and polysilicon solar cell, and little bit about the silicon manufacturing. Okay. So, thank you.